So welcome to an experiment, experiment L2, which is all about Snell's law and measuring the refractive index of a material like glass. I'm always going to explain it using an example, and the example I'm using is Leaving Cert 2020, question 2. So where do you find the notes to actually carry out this question? Well, if you go to your notes and go to Light and Sound, Lesson 4, Refraction 1, and we scroll down through these notes. Yeah. And here I get to an experiment to verify Snell's law and to measure the refractive index of glass. Again, there's a detailed explanation here, but you don't have to learn the explanation. You just read it to familiarize yourself, because they can ask you anything they like about the experiment. So it's important that you read the method a number of times. So the question I'm looking at is Leaving Cert 2020, Experiment L2. So they're saying to me in this question, in an experiment to determine the refractive index of glass, light was passed through a glass block, and the angles of incidence I and the angles of refraction R were measured for different values of I. They recorded the data there in a table. So what are they asking me in part 1? In part 1, they're saying, explain how the refracted ray and the angle of refraction were determined. And they're also advising me that a labeled diagram may help your answer. Well, we always want to draw diagrams when we can. It makes the explanation much, much easier. So let me have a look at this in detail. Now, this solution will be done for you in your notes. So you'll have a kind of a model answer. So all I'm doing here in this class is just explaining the idea to you, so you actually now understand it, and then you can write it in your own words. So here's a block of glass. You set that down on a piece of paper. You draw the outline around the block of glass. So you're left with a rectangle. So lift the block of glass away. I want to draw in an incident ray. So I'm just going to draw the incident ray as a red line going along the paper. So there's my incident ray. You're going to measure the angle of incidence, aren't you? Well, you always measure it with respect to the normal. A normal is a line drawn perpendicular to that edge. You'll use a set square for that. So the angle of incidence is the angle in here. Now the question is, how do I draw the refracted ray and how do I measure the angle of refraction? Well, this is how we do it. Take two pins and put the 2 pins upright in that incident ray. Put the block of glass back on its outline, and as a student you should look through the edge of the glass and take 2 more pins and try and place the 2 pins. Those 2 pins are in line with the previous 2 pins. So when I look through that last pin, all 4 pins appear to be in a straight line. Well, they're not actually in a straight line because the block of glass is bending them, but they appear to be in a straight line. Draw a line through these 2 pins here. This is called the emergent ray. Then trace the emergent ray back to the normal. And that there is your refracted ray. So you have to explain how you found that refracted ray. So when you're drawing your diagram, make sure you label it. And what's the angle of refraction? Well, it's the angle between the refracted ray and the normal. It's this angle in here. Let me just squeeze it in. There's my angle of refraction. So you've got to explain that using your diagram and then a couple of simple sentences. But the explanation is given properly in your solutions. Let's go on to part 2. So part 2, the question asks me, why would a smaller angle of incidence have led to a less accurate measurement of the angle of refraction? Well, a smaller angle of incidence will give you a smaller angle of refraction. So you will get a smaller value of ore. And when you're measuring smaller values, they have what we call a higher percentage error. So the percentage error in measuring that value of ore increases. And therefore your result is going to be less accurate. I mean, calling upon that statement, percentage error, is always a guarantee of getting marks. So 6 marks for part 2. Moving on to the next part. Well, the next part of the question is saying in part 3, use the data to draw a suitable graph to verify Snell's law. Now, this is really important. I mean, the one thing you have to know about every experiment is, here they are giving me values of I and values of ore. If you draw a graph of I against ore, you'll get a fat 0. You have to know what the suitable graph is. And the suitable graph actually is sin I against sin ore. Let me have a look at how you draw a graph in great detail, because this skill is very important. So I'm on to part 3. There are 12 marks for drawing a graph. You'll start off with full marks, and they'll take 3 marks off as you make mistakes. Well, first of all, here's the data from the table in the exam question. You have to know immediately, I need to turn that into sin I and sin ore. So you're going to get the sine of all these values. The sine of 30 is 0.5. You know how to put them into your calculator. How many decimal places will I go to? Well, I think 2 is good for now. 3, the graph probably doesn't have that kind of accuracy. If you go to 1 decimal place, maybe you won't get a very accurate result. So 2 is good. Sine 40 is 0.64. So put all them into your calculator and you get your values of sin I and sin ore. Now I'm ready to draw the graph. So here's my graph. Now what goes on each axis? Well, I suppose technically speaking, you should put sin I on the bottom because I is the independent values of the nice values. But it actually doesn't matter which way you put them, as long as you know what you're doing. I'm going to put sin I here and sin ore here. And the reason I'm going to do that is it's a bit easier to find the refractive index from the graph if I do it this way. But if you did it the other way around, fine, once you know what you're doing. What about my values of sin ore? Well, the first thing, of course, is every graph you know starts at the origin. When we do physics, start every graph at the origin. Sin ore, look at my values of sin ore. They go from 0 all the way up to about 0.68, 0.7. So I think I'll go up in 0.1s. I like to stretch everything out nicely. I don't want everything too cramped, but I also want it to fit. What about my values of sin I? Well, they go from 0 to 0.98, nearly 1. If I went up in 0.1s, it mightn't fit. If it does, you can go up in 0.1s. So I can go up in 0.2s. I don't have to go up in the same increments as I went up here. So I went up in 0.2s. So everything is nicely spread out now. You've labelled your axes. There's no units for sin I or sin ore. Because if there were units and you didn't put them in, you would lose 3 marks for leaving out something very important, labelling the axes. So let me put my points in. So it's sin ore down here. So my first point is 0.33, 0.5. So I go out 0.33 and I go up 0.5 and I get my first point here. Put in a dot, X, circle. My next point is 0.42, 0.64. Dot, X, circle. And so on. 0.52, 0.77. 0.57, 0.88. So put all your points in. I haven't done them all, but that's okay. You're also going to be more accurate because you're using graph paper. I'm doing it quite roughly. Here, it's very important you put the points in the right place. You'll lose 3 marks if you don't. So be very accurate. I can see here I'm going up in 0.1s. So every little square in here is a 0.01. And every little square in here, if I divide 0.2 by 10, I get 0.02. So make sure you put your graph together very accurately. Right, now that I've put the points in on my graph, the next thing is to get what's called a best fit. There'll be 3 marks for a best fit. It's good if you have a glass ruler, so you can see both sides of it. Anchor the ruler at the origin and put the ruler up through the points so that it goes through the middle of the points. You know, some points will be on, some will be slightly above, some will be slightly below. If you have too many above or too many below, you lose the 3 marks for your best fit. And then in one go, draw a straight line down towards the origin. So there's my straight line graph. I already know anyway what my graph looks like when I do this experiment. Right, moving on to the 4th part of your question. The 4th part is asking me to explain how your graph verifies Snell's law. That type of question is very, very common. And we'll say the answer in the same way every single time. How does that graph verify Snell's law? Well, what we say is the graph is a straight line passing through the origin. If that's the case, it means that quantity up there, sin I, is directly proportional to sin R. That's a statement of Snell's law. So we do this in a number of experiments as well, like Joule's law, Ohm's law, and so on. So basically my answer is the graph is a straight line. Passing through the origin. You know, I always tell my students to write this down anyway, whether they ask you or don't ask you. Just do it automatically. And therefore, you can say the quantity up here, sin I, is directly proportional. There's your symbol for directly proportional to the quantity down here, sin R. And that is a statement of Snell's law. I just put Snell's law in brackets like that. So that's a very, very common question. So I want you to be able to answer it very, very well. There's 6 marks for that. The last part they're asking me to do in our question is use your graph, part 5, calculate the refractive index of glass. We call the refractive index N. So we're going to do that by finding the slope of the graph. Because of the way I've drawn the graph, when I find the slope, it'll automatically give me the refractive index. So I'm going to find the slope of my graph. And the slope of your graph is lots of ways to write down slope. I always use rise over run. Make sure you show the work very carefully on your graph. So I'm going to take a value from sin R. Actually, I don't want a value from the table. So I'm going to pick a value. I think a value like 0.35. That'll work nicely. To take 0.35, which is halfway between 0.3 and 0.4, and draw a line straight up until it meets the graph. And then draw a line straight across till it meets the sin I axis. And mark these points. How far you go out? I went out 0.35. That's called the run. So the run is 0.35. And how far I go up from 0 up there, that's called the rise. I'm just taking a guess here. You'll be more accurate with your graph paper. And I get, say, 0.52. That's my rise and my run. Mark in the other point that you're going to use. The other point we're going to use is the origin 0, 0. So mark that point in and mark this point in here. This point is, how far did I go out? 0.35. How far did I go up? 0.52. So show 2 points on the graph of the straight line And that allows me to find the slope of that straight line. The rise is, how far did you go up? Well, if I want to be pedantic, 0.52 minus 0. And what's the run? The run is 0.35 minus 0. So I end up getting 0.52 all over 0.35. So I'm going to put that into my calculator to give me my refractive index, because the slope is the refractive index, because the rise is a value of sine I, and the run is a value for sine r, and sine I divided by sine r, as you know from the lesson, is the refractive index. So into my calculator, I'm putting 0.52 divided by 0.35, and I get about 1.49, probably 1.5, but write down 1.49 or 1.5. I'll write down 1.49, and that's equal to the refractive index n. So now you've done just about everything you need to know. So this is why I picked that question. Everything you need to know about Snell's law.